Silence doesn't just reduce sound around you. It reshapes how the brain decides what matters and what gets ignored. In a quiet moment, attention stops reacting to the outside world and starts reorganizing itself from within, changing how focus, memory, and even decision-making actually work. What feels like emptiness is often the brain shifting into deeper internal processing modes that are usually hidden by constant noise. Here on Relaxing Facts Studio, we break down how silence affects concentration, why some minds become sharper while others feel overwhelmed, and what this reveals about human behavior in modern environments filled with continuous stimulation. A person concentrating deeply on one task can lose awareness of nearby conversations, background movement, and even the passage of time itself. The brain shifts into a more stable attentional state during sustained focus. This process depends heavily on the prefrontal cortex, the region responsible for planning, decision-making, impulse control, and task coordination across multiple neural systems. Instead of constantly reacting to new stimuli, the brain begins suppressing irrelevant sensory input so cognitive resources remain directed toward a single objective. That suppression process becomes biologically expensive when interruptions occur repeatedly because the brain must rebuild concentration after each disruption. During uninterrupted work, neural activity stabilizes into longer cognitive sequences that improve problem-solving efficiency and information retention. Researchers studying sustained attention often describe this as cognitive persistence, where mental systems remain engaged without frequent task switching. Brain imaging studies show that sustained concentration reduces unnecessary attentional shifting while improving coordination between working memory networks and executive control systems inside the frontal cortex. Modern digital environments rarely support that stability for long periods because notifications, media feeds, and multitasking systems compete continuously for human attention. Earlier human tasks often unfolded in longer uninterrupted cycles, whether tracking movement, building tools, or navigating environments over extended periods. Many applications intentionally use variable reward systems, visual alerts, and urgency cues designed to trigger rapid attentional reorientation. The nervous system responds automatically because sudden changes historically signaled important environmental events. Even small interruptions create larger cognitive costs than most people realize. Some studies estimate that returning fully to a complex task after distraction can require several minutes of mental reconstruction. Across an entire workday, repeated interruptions can fragment concentration into dozens of incomplete cognitive cycles. Instead of maintaining smooth processing flow, attentional resources repeatedly stop, redirect, and reorganize under continuous sensory and informational demands. That fragmentation helps explain why quiet environments consistently improve high-level cognitive performance across writing, mathematics, engineering, and strategic planning tasks. Silence reduces the number of competing signals requiring active monitoring, allowing executive systems to maintain longer periods of stable processing. The human brain evolved to concentrate deeply under conditions where interruptions were occasional, meaningful, and limited, not under modern environments engineered to compete constantly for awareness. Cities rarely become fully quiet anymore. Engines continue through the night, ventilation systems hum inside buildings, and digital devices fill small pauses with constant audio stimulation. Modern humans now live inside nearly uninterrupted layers of background sound. For most of human history, environmental noise behaved differently, appearing in temporary patterns shaped by weather, wildlife, water movement, and human activity rather than continuous mechanical systems. That quieter sensory structure allowed the brain to detect subtle environmental changes more easily, especially during periods without immediate activity or danger. Those subtle changes mattered because the human nervous system evolved to monitor low-level variations in sound, movement, and spatial rhythm continuously. A distant branch snap, shifting wind direction, or sudden silence among animals could signal important environmental changes requiring attention. Neuroscientists associate part of this sensitivity with selective auditory attention, where the brain filters background information while remaining responsive to meaningful anomalies. Instead of separating occasional signals from silence, the auditory system now processes persistent traffic noise, overlapping conversations, machinery, and digital alerts that continuously compete for perceptual priority. Earlier environments contained sensory variation balanced by long recovery periods, allowing perception systems to recalibrate naturally. Urban civilization changed that balance dramatically. Industrial machinery, transportation networks, and electronic media transformed human sound environments into nearly permanent stimulation systems. People visiting isolated forests, deserts, or snowy landscapes often notice hearing distant sounds more clearly after several quiet hours because reduced noise exposure temporarily lowers sensory competition across the auditory system. Modern noise pollution now affects enormous portions of the global population, especially in densely populated urban regions. Environmental health researchers have linked chronic noise exposure to elevated stress responses, sleep disruption, and reduced cognitive recovery efficiency. Some cities maintain nighttime sound levels comparable to constant office environments even after midnight. A single apartment can contain refrigerators, traffic vibration, elevators, neighboring media, and phone notifications operating continuously across a 24-hour cycle. That permanent stimulation may be weakening forms of perception humans once relied on instinctively because sensory systems improve through periods of contrast, not constant saturation. Quiet environments help recalibrate attention, emotional regulation, and low-level environmental awareness by reducing unnecessary cognitive load temporarily. The growing interest in quiet retreats, noise reduction practices, and distraction-free environments reflects an increasing recognition that the modern sensory environment differs profoundly from the conditions under which human attention originally evolved. A faint sound in darkness once carried immediate survival value for early humans. Subtle movement through grass, distant footsteps, or changes in animal behavior could reveal danger long before it became visible. Human hearing evolved to detect environmental variation with remarkable precision under quiet conditions. The brain continuously compared tiny differences in timing and volume between both ears to estimate direction, distance, and movement through a process called binaural localization. That sensitivity helped humans navigate forests, track movement, and identify threats even when visibility remained limited or completely absent. That directional awareness depended on low-noise environments because the nervous system performs best when meaningful signals stand apart from background interference. The auditory cortex filters enormous amounts of sensory input automatically, prioritizing unusual or changing sounds that may require attention. Neuroscientists describe part of this mechanism as sensory gating, where the brain suppresses predictable information while remaining alert to unexpected changes. Traffic, machinery, media playback, and overlapping conversations create dense sensory environments that reduce the brain's ability to notice low-level environmental variation efficiently. Natural environments usually contain layered but intermittent sound patterns shaped by weather, terrain, water, and wildlife behavior. Modern urban environments operate differently. Mechanical systems generate stable, repetitive noise across broad frequency ranges for hours without interruption. Chronic exposure to persistent background sound can reduce responsiveness to weaker stimuli because sensory systems gradually deprioritize subtle signals buried beneath continuous environmental noise. Researchers studying noise pollution have observed measurable declines in attentional sensitivity under heavily saturated auditory conditions. The scale of modern sensory exposure is historically unprecedented. Millions of people now spend most waking hours surrounded by engines, electronic devices, HVAC systems, alarms, and media streams operating simultaneously. In large cities, ambient sound rarely drops to levels where fine auditory discrimination functions optimally for extended periods. Even rural areas increasingly contain distant highways, aircraft noise, electrical infrastructure, or constant digital audio exposure through personal devices. That loss of subtle sensory awareness may affect more than hearing because attentional sensitivity depends heavily on detecting small environmental changes efficiently. Quiet training practices used in meditation, wilderness navigation, and certain military exercises attempt to restore portions of that low-level perceptual awareness deliberately. Extended periods in quieter environments often improve directional hearing, concentration stability, and environmental awareness because the brain regains opportunities to process weaker sensory information without overwhelming background interference. A long stretch of uninterrupted quiet often appears in the routines of people who produce complex work. Writers close doors. Engineers use headphones without music. Executives schedule early hours before messages begin arriving. Silence is not treated as comfort in these cases, but as a working condition. The brain responds differently when external input drops below a certain threshold, especially in tasks requiring extended reasoning and planning. That environment reduces the number of competing signals entering working memory at the same time. High-level cognitive tasks depend heavily on the prefrontal cortex, which manages goal maintenance, sequencing, and long-range planning. When background noise and interruptions accumulate, that system repeatedly resets its context, which reduces efficiency. Neuroscientists studying attention stability often describe this as executive load fragmentation, where mental resources are split across too many partial tasks. Without constant sensory reorientation, the brain can maintain a stable representation of a problem for longer periods, which improves logical consistency and reduces mental fatigue during complex work. Most daily environments operate in the opposite direction. Open offices, digital notifications, and multi-device workflows continuously inject new stimuli into attentional systems. Each input may be small, but their cumulative effect forces repeated cognitive switching. Not because noise is inherently harmful, but because sustained reasoning requires fewer interruptions than modern systems typically provide by default. Even short periods of uninterrupted focus can significantly change output quality in complex tasks. Research on deep work patterns shows that longer uninterrupted intervals improve error detection, strategic planning, and creative problem structuring. Some individuals organize their schedules around protected blocks of time that eliminate external input entirely for 1 to 3 hours at a stretch. Whether in software development, scientific research, or financial modeling, extended silence often correlates with tasks that require multi-step reasoning rather than reactive decision-making. That preference for silence reflects a practical adaptation rather than a lifestyle preference. The brain performs differently when it can sustain uninterrupted cognitive trajectories instead of repeatedly rebuilding them after distraction. Over time, high performers tend to protect that state because it produces clearer outcomes with less mental depletion. Silence, in this context, functions as a productivity condition. It creates the stable neural environment required for complex thinking to fully develop without constant external reset. A quiet room does not feel calm for everyone. Some people become restless within minutes, while others feel an unusual sense of discomfort they cannot easily explain. In these moments, silence does not reduce mental activity. Instead, it removes external structure, and the brain immediately fills that gap with internal signals that were previously masked by environmental sound. Breathing, heartbeat awareness, and internal thoughts rise in intensity when no external reference points remain to balance attention. That shift happens because the brain depends on constant sensory input to maintain orientation and emotional regulation. When external stimulation drops sharply, the default mode network becomes more active, increasing internal thought generation. For some individuals, this leads to productive reflection. For others, it amplifies unresolved emotional memory, intrusive thoughts, or heightened self-awareness that feels uncomfortable. Neuroscientists also link this response to differences in sensory gating efficiency, where some brains filter internal noise more effectively than others during low stimulation states. In busy environments, external sound competes with internal signals, effectively limiting how much inner thought reaches conscious awareness. In silence, that competition disappears. The brain no longer prioritizes outside input, so internally stored material gains prominence. Two people can experience the same silent room, yet one enters deep focus while the other experiences mental tension or restlessness due to increased internal signal strength. Studies in sensory deprivation research show that even short periods of reduced stimulation can significantly increase activity in memory-related and self-referential brain networks. In more extreme conditions, the absence of external input can lead to perceptual amplification, where subtle internal sensations feel significantly stronger than usual baseline perception. Without external benchmarks, internal signals become the primary source of informational input, effectively reshaping what the brain treats as relevant reality in that moment. This variability explains why silence is not universally experienced as calming, even though it is often described that way in general terms. The brain's response depends on internal cognitive load, emotional history, and sensory regulation efficiency at the individual level. It is a shift in dominance, from external input to internal processing, and that shift can feel either stabilizing or overwhelming depending on how the brain manages its own internal signals. Silence reveals more about the human brain than constant noise ever could. It exposes how attention shifts, how memory resurfaces, and how deeply behavior is shaped by the environments we live in every day. What feels like doing nothing is often the brain reorganizing itself in the background, building clarity from reduced stimulation. If this episode gave you a new way to think about focus and awareness, thank you for watching Relaxing Facts Studio. If you haven't subscribed yet, consider doing so. Like the video, share it with others, and leave a comment with your thoughts. Your support truly helps the channel continue growing and reaching more people.